Welcome, everyone. Welcome to Stanford Data Science and our Fall 2023 Distinguished Lecture by Jeffrey Heer. My name is Chris Menzel. I'm the Executive Director for Stanford Data Science. We're a multidisciplinary unit spanning Stanford's 7 schools that focuses on data-driven discovery, accelerating data science and its applications to data-intensive scholarship, as well as advancing data science education at Stanford and beyond. We support early career researchers at both the PhD level and the postdoc level through our data science scholars and data science fellows programs. We also support faculty-led research centers on open science, causal inference, data-intensive sustainability science, and health with data science. In the near future, we plan to launch an ambitious effort that combines computational resources with research data scientists to help further accelerate data-driven discoveries across campus. As part of what we do, SDS, Stanford Data Science, brings communities together around data science topics that are of broad interest, just like tonight. And so, to kick this evening off, I'd like to invite up Russ Poldrack to introduce our speaker tonight. Russ is an associate director for Stanford Data Science, as well as the faculty director for our Center on Open and Reproducible Science. He is a professor of psychology using neuroscience and machine learning to study how the brain gives rise to adaptive human behaviors. Please welcome Professor Russ Poldrack.
Thank you very much. So it's my distinct honor to introduce Stanford Data Science's first distinguished lecturer of the school year, Professor Jeffrey Heer. Dr. Heer is the Jerre D. Endowed Professor of Computer Science and Engineering at the University of Washington, where he directs the Interactive Data Lab and conducts research on data visualization, human-computer interaction, and social computing. The visualization tools developed by Jeff and his collaborators, which I'm sure many of you have used, including Vega and Vega Lite, D3.js, Protovis, and Prefuse, are used by researchers, companies, and data enthusiasts around the world. Jeff holds BS, MS, and PhD degrees in computer science from UC Berkeley, who then betrayed to join the Stanford CS faculty in 2009. He then moved to University of Washington in 2014, where he's worked with students and collaborators to develop the Vega and Vega Lite visualization grammars. Along with Joe Hellerstein and Sean Kandel, Heer's also developed interactive tools for data transformation, including Data Wrangler, which led to the founding of Trifacta, which is a provider of interactive tools for scalable data transformation. Other research contributions include work on the graphical perception of visualizations, social data analysis, text visualization, and interactive language translation tools. Jeff's work has received awards at the premier venues in HCI and visualization, including ACM Chi, UIST, CSCW, IEEE Infoviz, IEEE VAST, and Euroviz. And other honors that he's received include MIT Technology Review's TR 35 in 2009, a Sloan Fellowship, Gordon and Betty Moore Foundation Investigator Award, an ACM Grace Murray Hopper Award, IEEE Visualization Tech Achievement Award, and induction into the inaugural class of the IEEE Visualization Academy in 2019. So we're lucky to welcome back to Stanford, Professor Heer.
Okay, can everyone hear me all right? Great. Thank you for that warm introduction, and it's great to be back for my 10-year reunion tour here on the Stanford campus, where I'll talk about a number of projects we've pursued over the years, tried to support data scientists in various ways, and then end up sort of backing up into the subject of augmenting those practices through artificial intelligence. Now, back in the 60s, McLuhan famously quipped, "We shape our tools, and thereafter our tools shape us." And in many ways, this talk will be a rumination on that idea, but in the context of data science and data analytics. And now, when I started my faculty career, that was actually when this quote came out in January 2009. The heady days when terms like data science and big data were new, fresh, entering the mainstream and not tired in the ways that at least big data is today. Hal Varian wrote this rallying cry for the area. The ability to understand, process, extract value, visualize, and communicate data, that's going to be the hugely important skill in the next decades. We now have essentially free and ubiquitous data, so the complementary scarce factors, really like the human factors, is the ability to understand the data and extract value from it. And indeed, as predicted, human society has continued to produce data at a rate faster than Moore's law, alongside which we can plot download counts of popular tools for data analysis, such as ggplot2 and dplyr for visualization, data transformation in R, as well as Jupyter notebooks. Meanwhile, here are master's degrees in statistics. We can switch to a log scale to see that trend more clearly. It is positive, don't worry. And while these measures are imperfect proxies, one does wonder, has the rise of data and corresponding tools outpaced the growth of corresponding analysis expertise? And so in the nearly decade and a half since this was quipped, some of our earlier optimism actually now strikes me as naive and neglectful in its consideration of potential harms. So for example, for whom is the data free? Everyone, or just those organizations with massive data collection capabilities? Data may be, in a sense, ubiquitous, but it also may be biased in terms of who it represents and how it represents them. And who decides what's valuable? Who benefits and who might be harmed by various data analysis projects? So for example, massive data collection can also enable massive data breaches and other unethical applications. And as we ponder this, note how we're being served up ads for machine learning and advanced analytics, throwing more fuel on the fire, potentially. And of course, meanwhile, a replication crisis is stirred in multiple scientific disciplines. And this raises questions around both analysis methods and incentives across research fields. And if these issues arise among trained scientists, what pitfalls lie in wait for users of so-called self-service analysis tools that many vendors, including here in Silicon Valley, including myself as a company co-founder, have tried to develop and market. And so from the outset, I think it's important that we reckon with the fact that people's interaction with data is subject to misuse and abuse. So let's consider a full life cycle of end-to-end data analysis. This process involves a number of phases, including, of course, data acquisition, transformation, exploration, modeling, and presentation. And though we might be tempted to view analysis as a linear progression, of course, real-world efforts typically look much more like this. Analysis is an iterative and interactive process, often involving moving back and forth between different phases and different representations, and also between conceptual, mathematical, and computational models. And so throughout this process, even experienced and well-intentioned analysts are confronted with a host of decision points and challenges that are necessary to deal with in order to arrive at more reliable or robust results. And so a question that has deeply interested me is, how might our tools help us to become better analysts? And what happens is our tools become more opinionated and seeking to provide analytic safeguards and proactive guidance, and in part by applying artificial intelligence techniques within analysis tools. Now, of course, AI is a contested and amorphous term associated with competing histories, methods, hopes, and fears. In this talk, we'll draw a lot on good old-fashioned AI, so basically constrained combinatorial optimization within logical systems, as well as, of course, statistical machine learning techniques. But in service of intelligence augmentation, that's our ultimate goal here. Rather than trying to fully automate analysis, at least my interests are in the way our tools may complement us. So that is, of course, as many here have also advocated, the use of AI to enhance and not to replace. And so our corresponding design challenge is to determine, quote unquote, regions of optimality and possible divisions of labor among directed and automated actions, again, here in the context of data analysis. And I'll note, these ideas are as old as AI itself. In fact, this quote here is actually drawing from Bar Hillel's writings on natural language translation from over 60 years ago. So both the challenges of data and the challenges of AI, actually, while contemporary, have over a half-century history that we can draw upon. And so with that introduction, let's start by considering visualization. So this is the use of graphical methods to better explore, understand, and communicate data. And as I've worked on visualization research for almost 2 decades, a central goal of my collaborators and I has been to build tools that help designers and developers craft interactive graphics. And this led us to create tools such as Protovis, D3, Vega, and Vega Lite, so various languages and frameworks for creating graphics. But let's take a step back and ask, well, how should we use these tools? What makes a visualization good? And obviously, I put this in scare quotes because it depends what you're trying to accomplish with the visualization. What's our goal? Are we seeking to explore a new data set, maybe just get an initial overview, to communicate findings we already have in mind? What questions and comparisons are central to our endeavor? And that kind of informs the data transformations and visual encoding decisions we need to make. Now, fortunately, there is a rich body of work that can help guide visualization design choices. And to skim the surface, let's have some audience activity. We'll engage in a quick experiment. So what I'm going to do is show you two shapes, and your task is to judge by which factor the larger shape is bigger than the smaller shape. So first of all, no computer vision algorithms. Don't put out measuring devices. Don't yell out the answer either. I'll say out some numbers, and you can raise your hand. So here we go. Compare the areas of these circles using only a quick visual judgment. How much larger is the area of the big circle than the area of the small circle? Raise your hand if you think it's bigger by a factor of 4. Exactly. Okay, thank you. 5. Great. Okay, 6. 7. Okay, 8. 9. I'm still going, people. 10 or higher. So notice the interesting breadth of judgments there. Now let's repeat the same task, but we'll use a different visual encoding. In this case, bars along a lined axis. Now compare the lengths of these two bars. How much larger is the big bar? Raise your hand if you think it's a factor of 4. Crickets. Okay, 5. 6. Okay, now we see some hands. 7. 8. Okay, 9. A couple with a big fall off. And then 10 or higher? Anyone? No one. So notice the much tighter distribution of responses to that question. In case you were wondering, the answer in both cases is actually the same, and it's 7. So you have to trust me, if you melt down those balls on the right, you will actually exactly match that area. And here, you can see that here. So it's interesting, right? From different types of encoding, it actually result in different accuracies or times involved in trying to make sense of that information, which is just one of many possible approaches to trying to quantify an effectiveness of an encoding. And so, for example, multiple research groups, including my own, have run similar experiments to assess how people decode information shown using different visual encoding channels. Here we see differences in error rates across common spatial encodings, such as position, length, angle, and area. And a lower value indicates better decoding performance. And subsequent experiments go even further, for example, looking at the effects of task or data distribution in addition to visual encoding decisions. But already we have some relevant evidence that might inform visualization design decisions. So for the task of comparing individual quantitative values, which is just one of many sort of small perceptual tasks we might consider, position and length outperform angle and area, which in turn roundly outperform color. And these rankings can guide the decisions of human designers, but can also be used by algorithms to help automatically recommend effective views. And so I want to share with you, kind of an aside, just one example of a redesign based on perceptual principles that I found really compelling. This was done by Michelle Borkin and colleagues while she was doing a postdoc at Harvard, studying visualizations of arterial decay that are used by doctors to make diagnoses and inform decisions, such as whether or not to operate. The visualization in the bottom left here, involving a 3D model and rainbow color map, is what the doctors were already using in practice. They had this available to them. The researchers then evaluated alternative designs that, for example, replaced the 3D model with a 2D schematic diagram, while also kind of opening up the 3D model of the artery to make it flat, while simultaneously also looking at different choices of color encoding, moving from the default rainbow palette to a perceptually motivated palette that then tried to better highlight the areas of concern. What was really interesting, though, was the study that they then ran with doctors at Massachusetts General Hospital with real analysis tasks, and these were the corresponding diagnostic accuracies. All these results were statistically significant. So you can see these large increases, both to do by changes of color encoding and changes from a 3D to a 2D schematic view. And kind of amazingly, these were actually additive. You hear going from around a 40% accuracy up to about 92%. And the point here is that appropriate visualization designs aren't just an intellectual curiosity. They can also potentially save your life, depending on what the decision task is, and is the visualization well aligned with the decision task or the judgment that you have to make. So I could keep going, but let's move along. So while perceptual insights like these, I think, are valuable for visualization design, they're only part of the story. It's not enough to consider individual charts in isolation. We also have to think about how people view and create charts in sequence in that process of exploring data. So how might we better support effective data analysis and exploration? Well, in my years teaching visualization and data science classes, I've noticed many pitfalls that students make, in particular while exploring data. I sometimes see people dive in without performing appropriate assessment. So for example, overlooking data quality issues in the process. I also see people fixate on specific hypothetical relationships, maybe falling prey to confirmation bias as they potentially overlook confounding factors. These and other situational biases, of course, have been mapped out in both psychology and the popular press. So the question is, how might we nudge people to more effective or systematic considerations of data, in this case, particularly in those early stages of getting to know a data set and properly explore it? And so in my own lab, Kaneet Wangsapasawat and Dominic Moritz and collaborators and I developed Voyager, a system that seeks to augment visual exploration by using a recommender system. So let's take a closer look at how this might work. So here we can load up the Voyager interface. And on the left, we have a data schema. In this case, a famous data set about cars, maybe boring, but familiar to all statisticians. Next, we have some visual encoding shelves, similar to tools like Tableau. If you may have seen those, you can drag and drop variables to visually encode them. And then on the right, we have a canvas where we can see visualizations. And at this point, we haven't specified what we want to see. Instead of getting an empty screen, we're actually treated to a number of summary visualizations of each column of our data set. So for example, we can see the cylinder counts of engines, which unsurprisingly are mostly 4, 6, or 8. But perhaps surprisingly, we see things like 3 and 5 cylinder engines that we might not have expected. So we can examine these, for example, see different regions where cars might have been produced. And then scrolling down, we can see some various quantitative distributions. We see distribution over time with this peak in 1980. And then we can maybe see the shape of various things such as mileage, displacement, and so on. Alongside these, we can also engage in direct manipulation. So for example, if I'm interested in mileage, I can go ahead and drag that out and then create a visualization manually. So here, visualizing those mileage statistics along the y-axis. And you see I get different recommendations in response. I'm visualizing unaggregated data above, but now I'm seeing some aggregate summaries below. I can continue, for example, to scroll down and then maybe expanding the search frontier by considering some bivariate relationships, maybe examining some outliers that come out from that, maybe getting a sense of some of curvilinear relationships between these variables. And I can continue along my way, and scrolling down, I actually arrive at a time series plot, which seems to suggest that mileage is improving over the years. And maybe this is particularly of interest to me. When I go ahead and I mouse over these little shelf icons here, you'll notice that the UI has changed up here, so now it's actually showing me how to construct this chart. So having seen this and then mousing over that, I can see, oh, this is where I would have to put the different elements to create this. And if I want, I can go ahead and click this icon, and that's going to pivot. And I'm going to make that view now my current focus. And now I'm getting additional recommendations in response to that. One of which is to now aggregate. And perhaps if I want to simplify the view for now and look at the aggregated data, this average mileage over years, I could go ahead and select that, pivot that into my new view here. And now, again, continue to get additional recommendations, in this case with additional categorical variables, breaking down into, for example, the number of cylinders or the origin. And in looking at this, I noticed something that might be bothersome to me. It appears that American-made vehicles have worse mileage than those from Europe and Japan. Now, one might then be able to make some cultural assumptions, of what's value to apply that. But let's not rush to judgment, because there may be confounding factors as well. So I can go ahead and select this view, and doing that, and it becomes the current focus view. And now I'm getting recommendations relative to that. So some recommendations don't have to involve new variables or transformations. They might involve different choices of visual encoding. And so as these lines begin to get plotted over each other, I might also want to inspect a trellis or faceted plot to break them apart and see them in isolation as well. But I can also select from the types of recommendations I might get. So in this case, for example, adding a categorical variable. And doing so shows me something interesting, that if I look at 4 or 6-cylinder engines, those differences between regions aren't salient, but rather it's the fact that, at least in this data set, all the 8-cylinder engines were coming from the American market, which was affecting those averages that I saw earlier. So this helping sort of sensitize me to some of the important covariates in this data set and hopefully inform subsequent decisions, whether it's for data cleaning or modeling and so on. So to recap, the key idea here was to augment manual exploration with visualization recommendations that are sensitive to a user's current focus. The goal is to support systematic consideration of the data without exacerbating false discovery. And towards this goal, we actually don't mind the data for correlations that might be spurious. Instead, we actually model a user search frontier and optimize for related chart specifications, seeded by the user's current focus. So the idea is to keep recommendations relevant to that current interest. Here, candidate charts are actually pruned and ranked using a formal model of design constraints and perceptual effectiveness, which can be trained from perception experiment results, just like we saw. And so underlying this, we have the Vega Lite specification language, which is a formal way to represent these charts. And we can search that space of visualization designs in order to try and support recommendation and revision. And we can use machine learning methods to guide their chart recommendations. Our training data here actually consists of pairs of chart, where one chart was found to significantly outperform another in experimental evaluations that we can cull from the research literature. We also authored an underlying knowledge base of visualization design guidelines, which serve as soft constraints for trying to score candidate charts. We then encode each visualization example in terms of the constraints it violates. So to make that a bit clearer, an example constraint might be that quantitative axes include a zero baseline. Of course, this is not a hard and fast rule, so we want to learn how strongly we should weight it relative to other concerns. Given this representation, we can then apply learning to rank algorithms to automatically recover our constraint weights, thus learning some trade-offs between charts from experimental data. And these weights are then used to rank candidate visualizations in recommender systems such as Voyager. We also evaluate this through user studies, comparing manual specification tool like Tableau to what we've done here. And so we found that Voyager led to over 4 times more variable sets seen and over 2 times more variable sets interacted with. And in post-study interviews, participants also shared their impressions. For example, the related view suggestion accelerates exploration a lot. And then I like that it shows me what fields to include in order to see a specific graph. Otherwise, I have to do a lot of trial and error and can't express what I wanted to see. So there's benefit for learning as part of what we see these recommendations can help provide. But my favorite quote is things like this. These related views are so good, it's also spoiling that I start thinking less. I'm not sure if that's really a good thing. And we'll come back to this point again and again in this talk. But having just kind of dipped our toes in the sea of visualization, let's turn our attention to data preparation and transformation. So here's a representative quote from an interview study we conducted years ago, back when I was Stanford faculty. We worked with data professionals, and one of them said, I spend more than half my time integrating, cleansing, and transforming data without doing any actual analysis. Most of the time, I'm lucky if I get to do any analysis at all. Depends how you define analysis. But in any case, do you notice something suspicious about this quote? Anyone? Yeah? Well, after years of sharing this quote, a common response has been, this estimate is much too low. People report spending more like 80% of their time on preparation and wish they only spent 50% of the time. And so at the time we were doing initially this work, issues of data wrangling felt like an elephant in the room of data work. Everyone was doing it, but not necessarily talking about it. Of course, fast forward a bit, though, and you can find folks opining now on the platform formerly known as Twitter that in data science, 80% of time spent prepare data, 20% of time spent complaining about the need to prepare the data. OK, so how might we assist this process of data transformation? And consider this data set published by the US Department of Justice. And while readable by a person, for example, using spreadsheet software, this data set will fail to load in statistics, database, or visualization tools. We need to suitably transform the data to enable downstream use. So various types of reformatting, as well as cleaning operations and other types of filtering or aggregation transformations, really common to this process of preparing data for downstream use. And so this is sort of a classic now for us, because it was over a decade ago, my student Sean Kendall, our collaborator Joe Hellerstein, and others, and I started exploring these issues in the Data Wrangler project. So let's look at how we might tidy up some data using our original Research Wrangler prototype. So here we've loaded that same data set I showed you earlier. And we've done some very shallow analysis and initially identified things like column and row breaks, which you can see reflected in this transformation script here. And now I want to go about the business of reformatting this data to make it palatable to downstream tools. Well, one of the first things I might see is that there are these empty rows. And so I might indicate my interest in that by clicking it. And you can see I get a simple suggestion and response, delete row 2. But I can also generalize by looking at the content of the data. For example, suggesting to delete all the empty rows. And this is accompanied with a visual preview that gives me a sense of what this transformation will do to my data set. This looks good, so I might go ahead and hit the Enter key. And this is then added to my transformation script, and I see the current sample updated in response on the right as well. Next, I might notice that things like header rows are embedded in the table, and I'd like to make those metadata. So I click that, get a suggestion to promote it to a header, and then get proper column names. But now I have these extra header rows I don't need, so I'm going to go ahead and select those, generalize the corresponding selection, and then again, delete these from my table to clean it up further. Now I get to some of the more interesting tasks one needs to do. Like I want to find these state names that are embedded in text streams and then actually have them as a proper categorically valued column. So to indicate my interest there, I go ahead and select the text for Alabama. I see I first get a simple extraction that's inferred just based on string position. But I don't need to read these suggestions on the left to see that it kind of fails on what I'm trying to accomplish here just by seeing the preview. So I can give additional examples, for in this case, selecting the text Alaska. And he now says I'm doing the proper thing, both visually, and I can then verify that by seeing the transformation description. Add this, and I've added this extraction. And as I'm doing this, you may have noticed other indicators, such as data type indicators along the top for like numeric or string data, and also these visuals that give us a sense of data quality. So for example, how many things parse successfully as numbers versus those that don't, how many empty values are in this column, and so on. I can also click rows and or columns to get transform suggestions, including how to deal with some of these missing values. So for example, I can interpolate now to fill in this data. And now I have the data set that I can almost use. I just now have these rows I no longer need from which I extracted the state names. So I'll start by selecting the text reported crime in. And initially, the inference is wrong. It thinks I'm trying to do an extraction. But I can further prune and guide that search space, in this case by indicating I want to do a deletion. And now the appropriate transformation has been inferred. I can add that to my script. And now I'll spare you the detail of renaming the state column, but otherwise I have usable data for downstream tools. Well, maybe I want to export this data, so I can go ahead and do that. And if the data was small enough to fit in this web-based UI, I could do that and just export it in a variety of formats. But oftentimes, instead, we actually want to work with a sample of a much larger data set. And instead, the actual object that we're producing is a transformation script. Here, it's represented in kind of a structured editor with pseudo-natural language. Here, we've kind of cross-compiled it to Python code. We can do that for SQL queries. We can do this in other languages and so on. And then generate a program that we can then run at scale across a cluster to transform much larger amounts of data. And so those were kind of the basic ideas we explored. We then went on in 2012 to found a company, Trifactor, where we tried to commercialize some of these ideas, building a product that involves both kind of rich visual assessment for data quality alongside these kinds of user-driven transformation recommendations I was just sharing. And so now in this traditional approach to data preparation, a user may author a draft transformation script in a programming language. They might then test that script on a small amount of data, and then visualize and inspect the results. And then based on that, then maybe have to kind of lather, rinse, repeat, so on. We sought to invert this process and approach that we called predictive interaction. So instead, the user starts with a visual interface to their data in which they can highlight values or features of interest. Given user selections as input, machine learning algorithms then predict potentially relevant transformations. So again, we're searching over a space of possible specifications here of data transformations, and then learning through machine learning ranking functions to then to try and decide among them. The system then visually previews these suggestions to allow a user to choose, adjust, or confirm the transformations that they'd like to apply. Now, the basic underlying principle from at least a user interface perspective is to provide a shared representation. So that is shared between the user and the system, by which people's input can proactively guide and build upon machine assistance. And then people can also, if necessary, review and edit the suggestions that are made. So how do you have this proper kind of cooperation between algorithms and analysts? And in user studies, we found this approach reduced specification time, promoted the use of reusable, scalable transformations rather than idiosyncratic edits. We also found evidence of complementarity. So that is, suggestions were good for tasks that people found hard, such as text extraction patterns and table reshaping. But on the other hand, people fared much better in cases where inference is less tractable, such as authoring an arbitrary formula. But similar to Voyager, we also saw concerns around user agency. Users appreciated suggestions in response to an initiating interaction, but did not always act on proactive assistance, which we also explored, often preferring to maintain the initiative. So as a third example, now let's turn to the task of authoring a statistical model. In the Tassan project, which was led by a recent PhD graduate, Eunice Jun, we look at a different form of shared representation. We have analysts first externalize a conceptual model of their domain consisting of hypothesized relationships among variables. One can then query for a specific measure, and then an interactive compilation process in which the computer asks disambiguating questions of the user then results in a corresponding statistical model that is intended by construction to be faithful to that given conceptual model. And the goal is not only to produce more reliable statistical models, but also to prompt users to more richly consider and communicate the conceptual models that they wish to assess. A key question, though, is how to elicit and represent a conceptual model that conveys sufficient assumptions about the data generating process. One usability challenge here is that, left to their own devices, the kinds of conceptual models that analysts express are informal and idiosyncratic. And here are 4 examples we collected in formative evaluations with various analysts, spanning diagrams and text, but as well as one participant who's like, I don't even know what you mean by a conceptual model, and skipped right to writing down a model formula in R syntax. And so looking at these 2 conceptual descriptions, they appear to differ on the surface, for example, diagrams versus sentences, but they importantly share some common types of relationships. And we like to provide a shared representation for expressing these conceptual models, which we might then use to generate corresponding statistical models. And in this, other works touch on these issues that we were inspired by, and this includes the description of process models in McElraith's Statistical Rethinking, which, if you haven't seen, is probably my favorite statistics text ever. And of course, the literature on causal models in the form of directed acyclic graphs developed by Peril and others. And so, as a starting point, one externalization for conceptual modeling, of course, can be to posit that one variable causes another. But interestingly, we ran user studies with analysts, including grad students in courses, as well as professional analysts, and actually found there's some surprising, perhaps human factors challenges here too, which is some people don't like using the word causes. Like, is this like this strong claim, perhaps? There's discomfort stating that one variable definitively causes another, even though understanding that this is hypothesized. And some express the desire to soften the claim, suggesting words such as effects or influences. But we didn't want to deviate from established terminology and possibly create further confusion. Plus, statisticians and computer scientists already have a terrible track record in diverging on what they like to call things. We didn't really want to play into that. So instead, we found actually additional annotations eased analysts' concerns while providing greater specificity. So for example, analysts wanted to know if a relationship was being assumed. So for example, was it established in prior work and they're just assuming this going forward? Or is it being hypothesized as part of their current study? And such annotations, first of all, provide more detailed documentation or externalization of their mental model, but also help them feel more confident in their statements. Nevertheless, we also observed plenty of cases where an analyst was initially uncomfortable stating a directional relation. So for example, does one variable influence the other, or is there an additional unobserved confounder you don't even know? And so if we instead allowed analysts to externalize this just as an association, basically in a relates predicate, this better reflected their state of understanding. But it also creates ambiguity. So for example, complicating an algorithmic process of mapping from the conceptual model down to a statistical model. And so in Tassan, we deferred this issue by actually permitting undirected relations, but requiring analysts to later engage in interactive disambiguation. And so, informed by such formative studies, Tassan provides a domain-specific language for authoring conceptual models, here expressed in the syntax of the R statistical language. This example actually comes from a freelance data analyst who participated in a subsequent summative evaluation. Specification maps to the following graph on the right in a graphical form. And admittedly, I would say this is a rather messy and ambiguous model, but nevertheless, it provides a useful externalization of that analyst's thinking. Again, it created a shared representation for reasoning. And so given this model, we might then query, and what we're querying for is a generalized linear model that will estimate the average causal effect of the chosen variable, here education, on a target variable, here income. And so put into that process, we then go into this disambiguation loop. When here's that you do this in, say, your notebook, et cetera, this comes up with an interface that then forces you to disambiguate what you meant. Which direction should the causal relationship go, alongside a visualization to help make that graphically clear. And then you move forward and then involve other things, including deciding amongst interactions. We can look at data types, for example, to make suggestions also around family and link functions in the case of generalized models. And we apply published best practices for covariate selection and, when applicable, random effects modeling. And the result is then a generalized linear model compatible with the disambiguated conceptual model that came through that interactive stage. Well, how does this play out in practice? Well, we conducted multiple evaluative studies, some with university researchers ranging from grad students to statistics professors, and later also with freelance analysts. People found that it aids expression of domain knowledge. So for example, we stated the formal structure made conceptual modeling more rigorous and more disciplined, and it gave them a structure in which to express themselves. And they felt that it also prompted reflection. That helped them think about more possible scenarios that might conflict with their current assumptions. So this isn't just a process of getting assumptions out of someone's head. Some of these assumptions are actively realized and formed through this process of externalization. How did this fare in terms of the models produced? Well, so far we found that this actually not only preserves analysis intent, but also produced models, at least with selection, like AIC, BIC scores, that were better equal to hand-authored models by those same analysts. And at this point, analyses created with Tassan have now appeared in multiple peer-reviewed articles, including both the human-computer interaction literature and in public health and policy. So going forward, I'm excited by many other possible applications of externalizing conceptual models. I think they may be useful for everything from helping form pre-registration, engaging in experiment design and power analysis. I think there's much more we could do in terms of assisting the creation of conceptual models, and of course, downstream of generating a statistical model and helping with interpretation. And meanwhile, I'll also just note we've developed many other projects for other parts of the analysis lifecycle, including profiling tools to assess data quality, languages and systems for authoring and visualizing the results of multiverse analyses, where one executes multiple analytic paths in parallel, then evaluates an ensemble of results. And then finally, also an error analysis, tools for more systematically documenting errors made by machine learning models. But at this point, I want to take a step back because across all of the examples that we've seen, as well as some of these other projects, they raise critical questions about how to best balance system automation and user control. I've heard some of you have been thinking about these various issues as we've come along. Automation can pose challenges to human agency. One risk is the loss of critical engagement and domain expertise, just like our Voyager user who worried that good recommendations might lead to thinking less. In addition, we know automated methods may not be sufficiently accurate, and of course we have to reckon with and work to prevent the consequences of poor models let loose in the world. But meanwhile, we as people certainly have our own limitations. We often have ambiguous intents in which our plan of action is not fully specified, and assistive systems may help. We don't scale well to repetitive tasks, and of course have our own biases and foibles. So for example, when we would lack a more systematic global view, it might lead us to overweight local information or things we heard recently. And so in an attempt to balance these automation and control and data analysis tasks, the projects in this talk explored a strategy of using shared representations and actions, so including data visualization and transform specifications, and coupled them with models for reasoning about people's capabilities and goals. So just to recap some of those shared representations, in Voyager, we have an underlying language for visualization design, Vega Lite, which is also reflected kind of isomorphically as a graphical interface with like a drag and drop interaction and the corresponding charts, as well as underlying design constraints amongst we might reason around which designs we might prefer. In the case of Wrangler, we had an underlying data transformation language, DSL's domain-specific language, that could be reflected both as code or as natural language, pseudo-natural language representations, and of course visual previews to try and assess what a transformation would do. And then meanwhile in Tassan, we had these conceptual models as a shared representation, but then went through an interactive disambiguation process to support algorithmic approaches to then generating corresponding statistical models. And so I would say each of these serves as like boundary objects that enable reasoning and editing by both people and machines. So it's the method of cooperation, again, between algorithms and machines. So we see this as a recurring design pattern for approaching human-AI interaction. But what's next? Well, we've made it pretty far into this talk without addressing another elephant in the room, which I'd say is the current frenzy of interest and concern around large language models. And so having done all this work, in the past up to most recently Tassan, my lab, we're certainly interested in both the strengths and weaknesses of large language models and understanding how we might better leverage them. And so I feel obligated to speculate on some of the ways LLMs might helpfully contribute to an analytical work. And so let's walk through some of these possibilities. One that we're currently working on is actually using LLMs basically to extend formal shared representations. Are there interesting structural or world knowledge representations that we can extract from language models, verify, and then use as a resource subsequently? So for example, in tools like Voyager and the underlying reasoning, how might we author visualization design constraints? Well, the ability to reason about code and natural language is one avenue here. As a human, I prefer statements like, do not apply a log scale to a field with non-positive values as a potential design constraint. But I can ask an LLM, and they can translate that, in this case, to the syntax of answer set programming for enabling logical reasoning. We've done some of this with our past work and actually ended up with cleaner code in some cases than we initially wrote. And even doing the reverse, ended up with descriptions as comments that were, in our opinion, better worded than what we originally wrote. And so as this sort of translation between different representations is a valuable tool. OK, but how might we go further and extract visualization design constraints, for example, from the research literature? This is some active projects that a new grad student in my lab, Will Wang, is playing with. And he took these idiosyncratic representations of visualizations, not even Vega Lite, in some arbitrary JSON format that some collaborators developed, threw them into GPT-4, and then asked them to do a differential analysis of those visualizations relative to some known design concerns. And particularly asked, for which charts will humans tend to show an underestimation bias and why? GPT-4 comes back, well, chart that we labeled up E2. And it gives a nice description. It uses an area rect mark with a linear scale for the length channel. It does seem to have a nice representation of these arbitrary specification formats. When estimating the average height of bars, humans tend to underestimate the average, especially when the distribution of data is skewed or has outliers. I think we can add a citation needed on there. However, we actually happen to know the literature, and this is exactly backed by a paper that was published within the crawling period of GPT-4. OK, well, let's ask a similar question. Remember, we asked for an underestimation bias. Which charts will humans tend to show an overestimation bias, and why? Exact same one. Now, you might say, oh, stupid GPT. Well, it turns out, we know the literature. There's another paper with a conflicting result. But we don't know, both of which should be in the crawl, but we don't know which one is being targeted. So I actually do think there's a lot of potential to try to kind of extract some of these representations into other usable forms. But I think we need to provide proper grounding, whether that's the text of a paper and seeing what is suggested by it, as opposed to maybe just relying on the kind of the weights without further grounding and prompting. So lots to do here, but I do think there's a promise in this work. Another one to consider is where natural language is itself the shared representation. So a natural example here would be something like the analysis of unstructured text. So for example, researchers in computational social science may want to identify recurring themes in unstructured text, such as political social media posts. And here, example analysis goals may involve quantifying recurring themes, such as accusations of corruption or statements of partisan animosity, or for example, the use of militant or violent rhetoric. And common tools today might be to do something like topic modeling or clustering to try and make sense of this, which produce as part of their output probability distributions over key terms. But then you have to engage in this interpretive loop is like topic 1, House Republican Democrats. You can look at more terms. What is this really about? Does it align with a theoretical construct that's actually meaningful to me and the analysis I want to pursue? And so I won't go into it. I have an entire body of work where one of my former PhD students evaluated topic models and found some of these gaps between the ways in which we'd like them to support analysis versus what they actually provide. I can tell you they require extensive interpretive work and often are misaligned with analysis goals. And so can we use the capabilities of language models to try other approaches to high-level text analysis? So we, here at Stanford with colleagues, I've been working on investigating methods for what we call concept induction, which we consider a task for synthesizing high-level concepts from unstructured text. We define concepts as natural language descriptions defined by explicit inclusion criteria. So for example, concept induction could produce outputs like government accountability or social justice focus, where each concept is defined by detailed criteria that can also be applied as a zero-shot prompt to a large language model. And so in contrast to existing methods, if successful, we should be able to aid interpretation, allowing users to focus less on interpreting lower-level outputs, such as distributions over keywords, and more on applying and extending concepts to make sense of data and engage with theory. And our Loom algorithm, which is developed by a Stanford PhD student, Michelle Lamb, as well as collaborators here, uses large language models to sample extracts from text. And this can also be guided by giving a prompt in terms of the types of themes you want it to focus upon. Cluster samples to batch-related content, and then iteratively synthesize proposed concepts of increasing generality. And we can also iterate this process to synthesize even higher-level concepts from initial concepts, and producing outputs such as this. And after this generation phase, we can then apply these concepts back to our original text data. And since these concepts include explicit criteria, we can use them to classify the entire data set and then visualize text corpora in terms of concept prevalence. And so here, this Loom algorithm surfaces examples that match a political party positions concept. And there are many posts written from one party's perspective attacking another party's stance. And we worked with domain experts to try and evaluate these tools, at least initially. And they've used this data in their prior research and published work. And they found the resulting concept maps were consistent with and even expanded upon their prior analytic work. But with natural language as the shared representation, Loom also allows analysts to create their own concepts and apply them to the data, kind of on equal footing with what the algorithm is producing. In this case, our domain expert added a new concept in just a few seconds to examine a concept of social distrust. This was interesting because ideas like social distrust might be hard to pick up on, but Loom extracted relevant examples that display distrust, even though the text doesn't explicitly mention distrust. And so there's much more to say here in terms of much more evaluation we need to do, but I nevertheless find it an interesting, promising approach. And again, looking at this case where natural language is that shared representation. Well, lastly, I want to mention applications to end-to-end analysis assistance. And some of you may have seen examples like this already, where you have a data set and you walk up to a suitable version of ChatGPT and say, hey, conduct and visualize a detailed graphical analysis on sales profitability in key cities. I say that all the time. Well, here the result is impressive relative to prior generations of models, certainly, but unfortunately still would not get very high marks in my visualization course. The plot has multiple questionable encoding decisions, and the subsequent text, which is below the fold here, states rather obvious things, such as pointing out which bar is the tallest. In other cases, models may produce things that are just flat out wrong. In this case, the LLM is actually generating Python code, running it, and then returning the results. And there's a lot of things, again, that are impressive about this, but using it to try and do analysis in a sort of zero-shot format is not quite there yet. And more generally, I'm interested in cases where that analyst has more agency. I'm not sure a conversational back and forth is the best way to go about this. And so we've been exploring alternative approaches, including integrating assistance within computational notebooks. So here we have a Jupyter notebook on the left, with this Python code for various data analysis tasks. And on the right, for example, we made it a little bit bigger than you normally would have it in everyday use, but we have a chatbot interface that also involves contextual links into what. So we wanted to explore the ways in which LLMs might provide assistance. That might be execution assistance, like I'm trying to do this task, can you generate the code to help me do it? But also planning assistance, like should you have considered additional covariates? Oh, by the way, did you know that you maybe made a mistake in your data wrangling? Or in a kind of a nod to multiverse analysis, did you consider the following other approaches to analyzing this data? Now, as you might imagine, LLMs aren't quite great at that, though they can provide useful help. And so what's actually going on here is sort of a classic evaluation approach in human-computer interaction, which we call the Wizard of Oz study. And so in this case, while the analyst experiences this notebook interface, behind the scenes we have a researcher, kind of like in the classic story, instead of this big scary thing, there's like a little person behind the scenes doing all the knobs and levers. But I should note we had many pre-written suggestions that were generated by large language models, and others that were then curated on the fly by this researcher. So LLMs were deeply involved, but with human curation and guidance in terms of the types of prompts. And so the goal is, through this, can we study how analyst assistance is received? What are the ways that it's useful and which are the ways that break down? In a context where we can assume a certain high level of quality in terms of what is being produced in terms of the recommendations. So here's some example of the results where we had people also rated whether or not they found recommendations helpful or not throughout this process. And you can see it's varied, but not very well predicted by the category of help, whether it was statistical modeling, interpreting results, or execution assistance. On the whole, people found it useful, but I think what's most interesting is what people did not find useful and why. And in most cases, people actually said, this is a perfectly fine recommendation, it's just not helpful to me. Either because it's not what I'm doing right now, or I'm smarter than that. This would be really helpful for a beginner or someone else. And so there's some interesting problems. People wrote, interesting, this is helpful. I didn't realize that skin tone rating was a combination of rater 1 and rater 2. So this is actually getting to operationalization of some of the variables and kind of a data preparation step in their analysis that alerted them to how to approach this. I should note the context here is about who gets red cards in soccer, which is famously used in sort of a multiverse analysis study that we built upon here. Others said, very often the suggestions aren't in line with what you're currently typing. Now you have to think about whether you want to take that direction or your own direction. In some cases, we might even disagreed about which direction they should have taken, but we want to maintain some agency. And there were a couple of times, it's very specific, for the chi-squared where I was like, oh yeah, that's a good idea. I didn't do it at the time, but I put a pin on it, so people might want to revisit it later. But again, these last ones, these are my favorite quotes. I feel like this friend was great, but it also made me this clicking machine rather than an analytical thinker. So again, we're seeing these kind of issues of perhaps over-reliance. And so looking at this, I think the biggest challenge is even once you get a large language model in a place that's providing reasonable guidance is really how do you manage the impedance mismatch, as it were, between the system and what it can suggest and what the person is currently doing and what their background knowledge is. And so some of the takeaways from the study so far have been kind of guidance on how to better promote effective assistance to analysts, including alignment on their current tasks and goals, trying to understand something about people's analytic background, what's their knowledge of different methods. So having much richer models of the user than we currently have. How timing and initiative are involved, and of course, how do we keep people engaged, and help foster appropriate trust. So I'd say there's obviously plenty of future work to be done here. We've begun to map out sort of the space of issues, both in terms of technical challenges and design challenges, but still much to do if this is actually going to be something that I think I would feel comfortable deploying for others to try and benefit from. And so some of those steps might include modeling analysts' know-how and their current focus, as we've alluded to. But also, how might we also, a future work idea, incorporate explicit shared representations? I didn't say it outright, but in the previous example, the shared representation was your Python code broken up into Jupyter cells. And clearly, that's a meaningful and important shared representation, but there's others that we might layer on, including some of the various techniques we saw earlier in the talk. And some of the ways to best incorporate those, I think, remain interesting and important topics for both design and evaluation. Speaking of which, I left out what I think is one of the most important future directions across any of these things is improved protocols for evaluation. I've often gravitated to things like time on task and overall productivity, but we have to look at more longitudinal aspects such as over-reliance, as well as, of course, deep evaluations of any new analytic techniques that we're trying to produce. And that, I do worry that LLMs could prove to be a Trojan horse, certainly if used inappropriately. So in addition to brittle prompts and hallucinations, these models can exhibit multiple social and inductive biases, and users may be prone to over-reliance. And meanwhile, a lack of control and transparency, particularly around cloud-deployed models, seem like a recipe for irreproducible results. And so I think all of these are challenges that we have to keep in mind and also try and approach from our evaluative frameworks. And so in conclusion, I think the future of assisted data analysis is exciting, urgent, and with many open challenges. And as cliched as it may sound, it's up to us to build the future that we want to live in. And I hope that future is one committed to human agency, learning, and skillful action. So I'd like to acknowledge the social and organizational support that made all of this work possible, especially the amazing collaborators and graduate students who contributed to the projects that I shared today. With that, thank you for your attention. I'd be happy to take any questions. Yes?
Yeah, hi. I'm not a computer scientist, but I've studied visual arts and history of art undergrad, and I've been a lawyer. I was a lawyer for many years, and I really agree with you. Clicking boxes versus reading are two distinct things. I'm curious about if anyone understands that Europe has issued Elon Musk a 24-hour mandate to get back to them on the misinformation that's on Twitter related to anti-Semitism in connection with the Hamas invasion of Israel. This is just data and related to X, and I don't know if people understand this, but also today, I worked at the SEC for 15 years in the Enforcement Litigation Department. Today, the United States Securities and Exchange Commission is a commission, just like the FCC or the FTC. But the rulemaking group at the SEC decided to reduce the amount of time that you have to report that you own 5% of a company. And this is related to his acquisition of Twitter. And he's being sued in the Northern District of California, which is a federal court here, because he's not sitting down related to a formal order in connection with his acquisition of Twitter. I think this is a timely time to mention this.
Okay. Thank you for the comment. Yeah.
Thank you so much for the talk. I think a lot of these tools look really amazing, but like how to operationalize them in practice, it will involve some data privacy concern. For example, a lot of organizations are very protective of their data, and it's really hard to imagine them having their data leave the wall, for example, like hospitals and stuff. So can you talk a little bit about like what additional work needs to be done in order to, lower the barrier and really allow analysts working with pretty sensitive personal data also enjoy the power of AI and make their work more productive?
Sure. I think there's a couple issues there. I mean, I think there's nothing that prevents the deployment of most of these tools within any of these environments. It's just you can't reach out. Like you're working on your local data, your organizational data. Now, some of the concerns might be if you are then observing usage to try and learn better recommendations over time, that could be a potential data leak. So certainly as we commercialize some of these things, we were in like the initial stages of the big data era where people were still doing on-premise deployments. And we were actually very data sparse. Like our ability to actually get real usage data was quite limited for exactly these reasons. But it really changes when you then go into cloud-based deployments. And we put in place a lot of different things where we would anonymize. We wouldn't touch the data, but even things like metadata, like column names, can be revealing. And so there's things that we have to do with hashing algorithms for all of that. So we could then try and observe usage sequences and try and learn better models, for example, to get better data transformations, but in ways that that clients were comfortable with. So I absolutely agree that it's an issue, but it's really about where does the data sit and where does it move, and having proper controls over that clearly part of what one has to consider in deployments here. Related to that, separate from data privacy, I think other deployment issues is just how these different aspects fit into a larger analysis work cycle. I do think that having to move between various tools can be jarring to people's experience, and so I certainly very much like computational notebooks, and so thinking about how some of these approaches might be better integrated into those existing workflows and tools. The fact that most of these also have a grounding in code, so you might engage with things graphically, but then get back code that you can put in revision control, that you can review, that you can edit, is one useful form of shared representation as well that maybe better aligns with lots of data scientist workflows. Thank you for the question.
Hi, great talk. So you correctly highlighted comments by folks who didn't want to lose their autonomy, didn't want to lose the ability to think about data. But what this will do is the same thing that happened when we just unleashed easier to use analytic packages. What will also happen is people who know nothing about analysis, this will enable them to do more and more sophisticated analysis, and they won't bemoan the loss of their own judgment and autonomy. In fact, we'll get more and more professional looking. I mean, this is the other danger, which you didn't point out, which is it will change the user base to a user base that's less sophisticated, able to produce yet more sophisticated analyses with that patina. And I'm just wondering where you see that end of the danger spectrum. It's changing the users and changing the kinds of analyses that are produced without the restraints that we might currently have.
This is a great question. I mean, the short answer is I don't know, but it concerns me as well. I've heard different arguments. So for example, no one's brought it up yet. Maybe some of you thinking this, you look at whether it's a tool like Voyager or even just a tool like Tableau that's maybe less recommendation driven. Like, isn't this just a giant visual p-hacking machine? And the answer, it can be. I mean, so is your R terminal, right? It depends on how you use it. And so the other arguments people made is like, well, are you doing something that is, would you do better off if you hadn't looked at your data at all? I don't know. Or if you're making, you're doing these sophisticated analyses and maybe you have undue confidence, is this affecting your bottom line? And are you catching that? Now, I think there's lots of, I won't go into these, but lots of research that people have looked at, including other types of safeguards, including inferential safeguards that I haven't talked about today, where there's active research. Things that I deeply believe in that I also didn't talk about today is various approaches to uncertainty visualization and how to better evaluate those. I think those are critical tools in this. Like we have to have a manager or a coworker who has the ability to do some guidance. And I think there may be other types of more automated guidance that are also helpful here. But I think we'll always have to be vigilant. I could go on, but I think that kind of summarizes my take on it. Important area for more evaluation studies, too, by the way, as I was mentioning earlier. Yeah, please.
Thanks. Super interesting talk. So I actually have a related question kind of about the user base in terms of thinking about, do you imagine building the same kinds of tools as this gets more sophisticated for inexperienced users as you do for domain experts and good coders? Like, can the same kinds of tools help that full range, or do you really need to think, are you thinking about this differently? How do we do that in the best possible way?
Yeah, I don't know if I'm at the scale, or scope to think about that broadly, but I think it does tie into some of the observations we had in that last Wizard of Oz study, where how do you establish common ground? This is something that we do as human beings, talking to each other. Like, I get a mental model of someone's capabilities, their interests, their goals, et cetera. Are there suitable ways of trying to communicate some of that or identify some of that to provide tools that might help with that gap? Like, if I'm suggesting Bayesian methods to someone who has no idea about what a prior is that a reasonable thing to do? One of the things that does interest me, and there's different approaches to this, but some are like creating new types of educational software, I think is really important. And part of what we butt up against in these projects, as we talked about tonight, is there are aspects of learning and education that can be baked into these assistive tools as well. And I think that's also a really important avenue to push harder.
Hi, thanks so much. That talk was really thought-provoking and wonderful. So naturally, if you're giving a talk in the data science program, you're going to take the POV of data scientists. And I was curious to hear, of course, your thoughts about the possibilities for augmenting data consumers. I know there's, been following the literature on interactive data visualization, not just for analysts and for exploration of data, but in the context of understanding existing patterns and data already analyzed and presented in some form, and how you think about maybe some of the approaches that you presented tonight in relation to how educated citizens might engage with complex quantitative information in more agentic ways.
Yeah, I mean, some of my favorite work along those lines has been to see what others have done with our visualization tools over the years, including the graphics team at the New York Times, at the Guardian, Washington Post, elsewhere. Certainly they deal with exactly this question: how do we take complicated things, and what's the right balance of interactivity, how to approach that. I do think there's a really important, I have a student who's starting to work on this exciting project on how do you start automatically generating graphics for a communicative purpose that maybe translate to static print fine for your research paper, but you can engage with in a more sequential, interactive way. Maybe it's introducing the axes and what they mean, then layering the data in, before then taking you maybe step by step through a couple observations that are annotated. There are various ways that we could make that easier. Obviously, that needs to be grounded in studies and is this actually aiding interpretation? I have some work that's about to be impressed about trying to make it easier to add reading augmentations to things like academic papers. And so I think this whole space is really exciting, and there's a lot of really great, exciting researchers in the human-computer interaction field who are working on this right now. So I'm hopeful that there will be some really nice progress in short order.
Hi, thank you so much for your talk today. You covered a whole bunch of things, right? So the thing you brought up before about data cleaning and that being a lot of the work data scientists, that hasn't really changed. And then you focused a lot of your talk on analysis and asking questions with LLMs and then answering questions through that. When you think about what you're going to focus on in the future, are you thinking about doing more of the data cleaning side, more of the analysis side, and why would you choose one of those sides if you had those?
I would say, you want the real honest answer? Yeah, it depends which student come to join my lab, what their capabilities are and what they want to work on. I mean, I'm interested in all of those things. I do think and this has come up in a lot of my conversations here today and yesterday. I think what LLMs might do that's also interesting is that for certain tasks, it moves the level of abstraction in which we can talk about what we're trying to do. That was kind of obvious, hopefully, in the concept induction idea. Is like, well, we want the level of abstraction to be at this concept that we recognize as such that we can then work with. But within data cleaning, but also analytics tasks, like, can I state what my goal is? What is my intention? And whether it's through an LLM or through other means, can I then ground that into more concrete actions? Like, what are the corresponding queries or models or visualizations that are appropriate and supportive to that task? That's what I do see. The more interesting startups that I've talked to, and these that's the tack that they're taking. It's not just like, hey, we can autocomplete this SQL query or something else. It's more like, what is a higher level form of expressing what you want to do and then being able to provide useful results there. I think there's a lot of work necessary to do that well, but I do think that is an exciting possibility that seemed much further away only a year or two ago than it does today.
Hi there, thanks for the talk. So you mentioned a lot of the future directions of your research center around LLMs and their applicability to data science pipelines. Now, there's a lot of controversy and regulation in the world right now about how these LLMs should be made accessible, the regulation around them, whether they should be open source. As an academic working in this area, interacting with LLMs, maybe in sensitive settings, do you have any, positions on open source access, and how do you interact with LLMs? Do you work with the API that OpenAI provides or another large private AI organization, or are you working with open source models?
Yes, so great question. Currently, the experiments we've done so far have been with kind of cloud-based APIs, which I think has been useful, certainly in terms of their accessibility and our ability to do some experimentation. But as I alluded to earlier, I also do have big reservations about thinking about, well, if you get out of the lab into actually trying to deploy useful analysis tools, what's the computational cost, the carbon cost, the reproducibility, the control, et cetera. So, I think these are all very valid issues. I don't have, I'm not as knowledgeable in terms of what should be, for example, regulated and in what way. I'm not sure in what, how do we best quantify the harms while also enabling kind of productive academic use so we can better understand both the benefits and the harms I think are important. But I certainly am supportive of those efforts and try and keep an open mind. And so I would, after this public Q&A session, if folks have ideas on how you think we should approach it, please come tell me. I would love to chat about that more.
Hi. Thanks for your talk, really insightful. I'm Meghna, I'm a data scientist myself, and there's been a lot of discussion about this online, but these tools, while really helpful, will certainly change the responsibilities of a traditional data scientist today. Mm-hmm. And how do you sort of, foresee tools like this impact the job market, the landscape, and what kind of skill sets should someone like me be working towards or adapt as things like these come to market, these tools come to market?
Yeah, I think it changes our relationship to work and tools. But I kind of think of maybe to do an analogy, maybe we do less writing, but boy, we need to be better proofreaders than we did. And so I do think, and this is why I want to get back to the other point. I think that the educational benefits and how we explore those is also really important. How these tools can actually help people upskill, also connect to other things are quite important as well. And so I do think having a rich human understanding of what you're doing and why is important. And part of what any sort of automated or semi-automated assistance should be part of sort of the objective function of the design of those tools. It's not just get the job done faster. There are others who will disagree with that, but that's certainly the perspective that I have coming into this. Yeah.
Hi, thanks so much for the talk. You mentioned that you're very interested as well in visualizing uncertainty, and I was wondering if you could give us a little sneak peek into that research area. Because
there's a wonder. I'll just give you a set of names of people whose work I really admire. So Jessica Holman at Northwestern, as well as our colleague Matthew Kay, who, if you work in R, he also released the package ggdist for doing distributional visualizations. Alex Kao, who's at the University of Chicago. Les Padilla at Northeastern is a psychologist who studies uncertainty representations. All really look at their papers and work. It's really great. Yeah.
Yeah, I guess another audience you're speaking to, Jeff, is educators who teach students data science. And I'm assuming you have the same challenges. Obviously, the last year has forced us to completely rethink many aspects of data science education. And I think an interesting undercurrent of your talk is like the inductive bias of what we think good methods are, complemented by automated delivery of code or even suggestions of what to do. I'm just curious if you have, guidance for educators kind of living through this period. How would you suggest changing data science education in the classroom? Ranging from like novel approaches, taking advantage of LLMs, up to just certain things we shouldn't teach anymore. Curious to hear your thoughts.
Interesting. The idea of not teaching things anymore, at least the things that come to my mind, I find very troublesome. And that, what is it? I still think there's foundations that you have to build up in understanding. Obviously, there's basics of probability and statistics, of visual encoding, but also all of the issues of what can happen if the data is not what you think it is. Those don't go away. And so, while I do think that the tooling is going to change, I do think maybe it's interesting to think about, educators might play a really valuable role in how do the tools that are coming, what types of explanations or rationales should they provide to allow other audiences to try and do that proofreading. So maybe that's one educational skill. Here's an analysis generated by a tool. What's wrong with it, or how might you improve it? So generating some of those skills, and then along the way, what are the types of kind of reports or whatever additional annotations, what have you, that would aid that process? I think are pretty interesting to consider as well.
Hello. Yes. So I think obviously, data science is difficult, right? Otherwise, there won't be this room for professionals in here. But I want to take a step back, right? There were discussions about when these tools are super useful, and if it falls in the hands of a novice, it caused something. It wasn't outspoken loud, but something bad could happen. It sounded like. But I want to flip it around, right? Why can't the tools be much better, I suppose, so that data is not this so difficult, easy to make mistake kind of thing to people?
Yeah. That's a great question to try and unpack maybe some of my assumptions that have accrued over years. I've just found that there's so many things in interpreting data that as incredibly important as formalisms are, statistical modeling, thinking about causal inference. These are really exciting. There's so many socio-technical problems too in terms of where did this data come from, how do I interpret it, what needs to be done in terms of my task that I think are often external to what you could do just from a data and algorithm. And this is starting to be challenged by models that maybe have some more world knowledge, but I still, at least for me, my explorations are early enough that I don't trust them. And so, while I do think there can be benefits, and that's why hopefully I try and balance promise and peril in the way that I talk about it, I do have those concerns, and I think they're warranted. Yeah.
Thank you for your talk. It was very enlightening. The question that I have is, I'm an aspiring data scientist myself, and I'm just wondering, in terms of the optimization of effectively analyzing data and very large data, right? And since you're a data scientist yourself, do you think that we have certain factors or blind spots, you could say, that we are overlooking in this industry in the future that might cause problems later? And could you please speak more about that?
It's a big question. So, reflect on what you don't know. Negative space is a useful rhetorical concept. I think one thing that, I don't know, I've had a couple different thoughts. I don't know if it speaks to this, but this maybe I'm trying to ground this in experiences that, that your comment resonated with. I mean, one is that I think, I think I've definitely seen what I would call like maybe the tyranny of small data, where like people don't, like you have to have your own perspective, values, and belief, and you have to try things out. And sometimes people have a small amount of data, particularly in, statisticians don't always make this problem, but like in business context, like I'm going to cling to that data and use that to drive decisions. And like you're better off in those cases maybe just not looking at data, like sticking to your guns until you get to a better position and you have more experience and information under your belt. That's one. Another, and this is maybe more from the peak big data era, but just the idea that if we can collect more data, and I think this applies to LLMs as well, like, oh, we can just solve the problems and figure it out. Like you can somehow magically infer things, from a data set that actually the data collection may not support. And so when I think about that, it's like who's not being counted in the data or who's being represented, improperly, and the idea that if we just got more, you mentioned the thing of scale, that somehow those problems will go away. I thought that was I thought it was foolish then, and I think it's been proven hopefully foolish now. With LLMs, similarly, I wonder like, well, not only what is it being trained on, but do I want the most probable thing, or do I want, for some definition of task, the best thing? And how far apart are those? I don't know what various manipulations or weightings of different data sources go into some of the trainings of these models, but that's obviously going to affect what they produce. And so I think the lack of transparency in terms of what goes into a lot of these models is certainly a concern if we want to think critically about them. I do think that in the case of LLMs, at least the movement towards certain open source models by various organizations might help with some of that, so we can maybe get a better sense of what some of those blind spots are. Because we can't even start to inspect it, it's going to be very difficult to figure that out.
One more question.
Yeah.
All right. Hey.
Oh, I will.
So I was thinking about how your research is very focused on system building as opposed to, say, theory building. But at the same time, you also do a lot of very cool qualitative analysis and interviewing for all of your tools that presumably is contributing towards some notion of a theory of the human factors of visualization as contextualized by when people use your tools. And so I'm curious sort of how you think about the theoretical aspects as you're doing your system building. Like what are the once we move past all this low-level perceptual stuff, what are the interesting frontiers of the theory of the human factors of visualization?
Yeah.
And how do you think about the relationship between your qualitative analyses and kind of the broader theory? Are you trying to contribute to that? Or are those sort of more localized, or just like evaluating the human factors of your tools in isolation?
Yeah. So all of that is, I think, spot on. We've done a lot of empirical work as well. I mean, I hinted at some of it today. But the way I approach systems, particularly in visualization, so today, it's trying to take maybe impoverished forms of theory, but it's putting theory into an operationalized form. And a lot of what we're doing is actually trying to can we actually then make theories testable? In fact, I have a whole NSF grant that we're writing right now that's an extension of some of these things to other considerations, whether it's richer consideration of the differences in data or ways of trying to at least begin to formalize aspects of task, starting with perceptual things, but then trying to work up into higher ones and enable reasoning about that. So it's very much in conversation with theories that both ourselves and others have developed, but because I really like concretizing things. So one of my research mentors was Stu Card, who ran the user interface research group at Xerox PARC for years. And he once quipped to me, he's like, I never want to be in a room where someone is more reductive than I am. Which is funny, because you usually hear this as like this sort of derogatory thing, and it wasn't like he doesn't like theory or like big thoughts, but it's like, no, I want to be able to work with this concretely where I really understand the thing. And so a lot of, I think, maybe the intellectual itch that I'm not articulating is I want to, even if, again, if it's initial form, start to actually instantiate some of these theories within working systems. And the hope is then you can kind of turn around and see the weaknesses of the representations that we make in these systems and hopefully use that as ways to help advance or change some of our theory. And so I tend to bounce back and forth a lot, but yeah, I appreciate the question. Thanks.
All right, let's give a round of applause for our speaker.
Thank you.
Thank you so much for joining us today. I just want to take a moment to thank the folks that made this all possible, including Elizabeth Wilsey and Charlene Zelnis, and Stanford Event Services, Conference Services, and Stanford Video. So thank you all for coming tonight, and a big round of applause for everyone.